This is going to be the second part of Chapter 3 lecture. We're going to be going from 3.8 down to 3.15. So what are we looking at? Previously here, we had been looking at radioactivity, properties of nuclei and particles, antimatter, and things of that sort. So now we're going to start looking at how to describe decay. And we're going to be looking at radioisotopes and how quickly or how slowly they may end up losing or emitting radiation. So obviously, a lot of you know that radioisotopes are used in therapy. So it's not possible to predict when a specific nucleus in a radioactive sample is going to decay. Quantum mechanics can be used to predict the probability that a given nucleus will decay, but usually the probability of decay per unit time for a particular radioisotope is measured rather than calculated. So suppose that we have a parent radioisotope, and we're going to call that X, that decays to a specific daughter, and we're going to call that D. We would like to know the number N of nuclei X at any particular time T. That's why N is a function of T. The physical expectation is that we start out with some initial number of nuclei, and that the number decreases with time until after some long period of time, there's going to be no nuclei left. So let's assume that we know the number of nuclei initially present, and we're going to call that n sub 0 or n naught. It would seem reasonable that if we had two samples of a radionuclide, with one sample having twice as many nuclei, the number of decays per second will be twice as large in the larger sample. That does stand to reason. So this suggests that the number of decays per second is proportional to the number of nuclei present in the sample. In other words, the number of decays per second is going to be proportional to the number of atoms that we have. It is also true that the number of decays per second is equal to the negative of the rate of change of n, where delta n is equal to the final minus the initial value of n, and the change in time is the elapsed time. Minus sign is necessary because the rate of change of n is going to be negative. In other words, we're going from a larger to a smaller volume. And so when we put in the change in n, the minus sign there helps to correct for that. So the change in n over the change in time is proportional to minus n. Putting in a proportionality constant to make this some roughly equal, then the change in n over the change in t is going to be equal to minus lambda times n. The proportionality constant is also called the decay constant. It's characteristic of each particular radionuclide. So it's you have to figure out which nuclei you're dealing with in order to be able to tell what that decay constant happens to be. And the rate of decay is going to be governed by that constant. So the larger the value of lambda, the more rapid the decay. And the units of lambda are going to be 1 over time, expressed in whatever the units of times are, you know, seconds, hours, years, what have you. So the rate of change of n divided by n, and all of that divided by delta t is going to be equivalent to lambda. In other words, if you divide both sides by n here, that's pretty much what you come up with. So it can be thought of as a fractional amount of decay per unit time for small fractional decay. We'll get to a section here that if you know calculus, you can sort of see how all of this fits together. If you're not familiar with calculus, then the amount that you see of the nuclide is going to be equal to the original amount times this function of t. Now, in general, we're not really interested in the number of atoms remaining in a radioactive sample. There's no easy way to measure that. And so what really good does it do you to know that? What we are interested in is the rate of decay, or equivalently, the number of decays per second. Note that the number of decays per second is not necessarily the same as the number of particles emitted per second. So again, here's the derivation of the formula. You can go through that if you wish, but it's not necessary to do so. The number of decays per second is going to be called the activity. We're going to write that in as A. So it's the change in N over the change in time, which, as we've already discovered, is minus lambda N, which if we take the absolute value of it, is just lambda N. And therefore the activity is going to be equal to lambda times N naught times this function of T. Rewriting the formula there to involve just A. So A is equal to A naught times this particular formula. This, of course, has the same form as the equation for the remaining number of remaining nuclei. The SI unit is going to be a decay per second, or a becquerel. The old unit of activity was the curie. Curie is approximately the activity of 1 gram of radium. 1 curie is 3.7 times 10 to the 10th becquerels. The curie is a very large unit, so millicuries and microcuries are often used in its place. Although the becquerel is the standard SI unit, it is common to see these activities quoted in curies. So you can see here for low dose rate brachytherapy, microcuries are used. The activity is roughly 10 curies for HDR brachytherapy afterloader. And for a cobalt-60 teletherapy source, you're looking at 10,000 curie. Not something you really want to be exposed to. So again, this rule of thumb here, 1 millicurie is equal to 37 megabecquerel. So a sample containing a radioactive isotope may contain a stable isotope of that particular element as well. And when stable isotopes are present, they are called carriers. When no stable isotope is present, the sample is said to be carrier-free. The specific activity is defined as the radioisotope activity divided by the total mass of the element present, including any carriers. The specific activity of radium is about 1 curie per gram. Iridium-192 sources, which are prepared for HDR use, have a specific activity of about 450 curies per gram. And that is a very high specific activity, and it makes this isotope well suited for a remote afterloader. And the reason is the source can be made small and still retain a fairly high absolute activity. So now let's take a look at half-life. The half-life is going to be the amount of time it takes for half of the original sample to decay, or equivalently for the activity to become half of its initial value. The half-life is an intrinsic property of a radionuclide. It is independent of external temperature, pressure, chemical bonding, because none of these have any effect on the atomic nucleus. So the rate of decay of a radioisotope is related to the decay constant. The larger the value of lambda, the more rapid the decay, and hence the smaller the value of the half-life. We expect that the half-life and lambda are inversely related, and they go through developing a relationship to show that. So you can see here A is equal to A naught times E to the minus lambda T if you go through, you can compute that half of this remains when it hits the time of the half-life. If you go through and do some simplification, you can find this. Taking the natural log of both sides and eventually solving will get you down to this. So you can see here that how we come up also with the activity in regards to the half-life. So what this is trying to show you is that the amount of activity that you have now is going to be equal to 1/2 times the original value for, however many times or whatever the number of times is that you have that done. If you have several different, if you wait through 3 different half-lives, then the amount that you have left will be this times this raised to the 3rd power, and so on and so forth. So as far as a fraction of the original activity, you'll see this stuff start to tell you how quickly that's going to fall off. So here's a specific example. Let's say you've got an isotope of I-125, and that has a half-life of approximately 60 days and an initial activity of 10 millicuries. So what's the activity after 30 days? So knowing the hard way, you can say, well, I know what the approximate half-life is. I can go through and I can substitute that into this particular formula. I can figure out what lambda is. And I know the initial activity here. So I know that, and I can put it into this particular formula to determine the activity at 30 days. And this is what you come up with. If, however, you want to go with the method that they had before, where you have a naught over 2 to the n, depending on how many half-lives you have this going through, number of half-lives, since you're waiting 30 days and the half-life of 60 days, the number of half-lives that you have at that you're measuring it at is actually going to be 1/2. So if you go to this particular formula, you know that 10 is what you started with. You take 2 to the 0.5 because that's the amount of time that you're waiting on. You come up with 7.1 millicuries, about the same thing as if you ran through and you did the actual formula. And they're saying here solution number 3 is if you consult figure 3.3, which is this right here. T of, little t divided by the half-life is going to end up being 0.5. A divided by A naught is 0.71, and therefore A is going to be equal to 10 times 0.71, which is going to be equal to this. And this is because you know that A naught you can put over here. You know that you're going to, or multiply it by the 0.71. You know that you started with 10 millicuries. This is what you end up with. If we're going to look at example 3.2, and then we see that a source has a half-life of 12 hours and the initial activity of 10 millicuries, what is the activity after 3 days? So 3 days is equal to 6 half-lives. Therefore, n is equal to 6. We put this into this particular formula. A is equal to A naught times 0.5 raised to the n power. Plugging all that in, we come up with 0.16 millicuries. The radioisotope of iridium-192 decays at a rate of 0.94% per day. So what is the half-life of this isotope? You want to do it the hard way. After 1 day, there's going to be, subtract off 0.94, you got 99.06 remaining. Therefore, n divided by n naught is 0.9906. And this is going to end up being equal to e to the minus lambda, taking the natural log of both sides, so you can get at the exponent here. Get you the log of this is equal to basically the natural log of e to this, but the natural log of e is just going to be 1. This part up here comes down to become a coefficient. So lambda is equal to this. And then the half-life is going to be this divided by lambda, or 73.4 days. In this particular case, we also know that lambda is equal to the change in n divided by n, and all of that divided by t, which we know is 0.0094% per day, because we know that's what the decay rate happens to be. Knowing all of this information, again, when the change in n divided by n is going to be much less than 1, we can use this particular formula. This tells us what lambda is. We can put it into this particular formula and therefore generate the answer there for the half-life. So a radioactive source has an initial activity of 10 millicuries. After 3 days, its activity is 0.16 millicurie. What is the half-life? We know this is the activity initially. We know that after 3 days, it is equal to this. Okay. So if we substitute in all of the numbers, what we find out here is that 10 is equal to 0.16 times e to the minus 3 lambda. If we divide that in order to solve for this, take the natural log of both sides, we end up with minus 3 lambda is equal to this. Lambda comes out to be 1.38 per day. And since we know what lambda is, we can go through and we can determine what the half-life happens to be. So here's a clinical example. So you got a patient treated on a Monday with radioactive iridium-192, and it's using a high dose rate remote afterloader. The treatment duration to deliver a given dose is 289 seconds. You're going to treat them again on Wednesday. Say it's a cylinder, and this is coming back for the second treatment. The dose to be delivered is the same as on Monday. The activity of the iridium will be lower on Wednesday. Therefore, the treatment time must be increased. So what should the treatment duration be? Well, the decay, and we know what the half-life is. The decay of the activity is going to be given by this, where n is equal to 2 divided by 74, or this. Therefore, the ratio of A to A naught is going to be equal to this, or 0.981. So the activity of the iridium is 98.1% of what it was on Monday. Therefore, the treatment time needs to be increased by that particular factor. So you take whatever the time happens to be, divided by 0.981, and you've got to increase the time by 1.9%. So taking this, multiplying by 1.019, you come up with 295 seconds. So here in section 11, we're going to be looking at the mean life. It's useful for determining the radiation dose delivered by radionuclides for permanent implants. Permanent implant is a radioisotope that's being placed in a patient's body and left there permanently, like a prostate seed implant. If the activity were to remain constant at the initial value, how long would it take a sample to completely decay? So let's denote this time by Greek symbol tau and call it the mean life. And let's work at an expression for tau. So the number of decays per second multiplied by tau is going to be equal to n naught. So the number of decays per second is the same as lambda times n naught. And then tau is going to be 1 over lambda. So the value of 1 over the natural log of 2 is 1.44. So we're kind of simplifying this to say 1 over tau is the same as 1.44 times the half-life. And a useful equation for solving problems is A naught times tau is equal to N naught. So a patient receives a permanent I-125 implant. The total dose received by the patient is proportional to the total number of disintegrations. This will be, we'll explain that a little later. Given that the half-life is 59.5 days, calculate the total number of disintegrations if your original activity is 10 millicuries. So the total number is going to be A naught times tau. Tau is going to be 1.44 times the half-life. It's given us the half-life. So we know it's 7.4 times 10 to the 6 seconds. We know what the initial activity is. And we know that 1 curie is equal to 3.7 times 10 to the 10th decays per second. We know that 10 to the minus 2 curies is 3.7 times 10 to the 8th decays per second. So the total number of atoms that we have here, or disintegrations, I suppose I should say, is 3.7 times 10 to the 8th decays per second times 7.4 times 10 to the 6th seconds, and it's 2.74 times 10 to the 15th decays. So what sort of modes of decays do we have here? Well, we have an alpha decay. The equation for that is you've got your parent, and then you've got the daughter nuclei, which is left over. It's now missing 4 nucleons. It's missing 2 protons and 2 neutrons, which are carried away with a helium nucleus. This is common for heavy isotopes. An example is radium-226 going to radon-222. The alpha particles emitted in the radium range with a single kinetic energy of about 4.8 MeV. The range in kinetic energies of the alpha particles emitted in alpha decay of various radionuclides is anywhere from 4 to 9 MeV. For any given radioisotope, the energy of the emitted alpha particle is always the same. The distance traveled by the alpha particles is very small, just a few centimeters, or a few thousandths of a centimeter if it's in tissue. Alpha particles are not usually used for therapeutic purposes because their range in tissue is just so small. The exception is systemic radiotherapy, where alpha emitters are situated within cells. In any radioactive decay or nuclear reaction, certain quantities must have the same value both before and after the process. So a charge must be conserved, and for that reason, the sum of the subscripts must be the same on the left and on the right sides of the reaction equation. So in the equation for alpha decay, we have Z on the left side and we have Z on the right side, but you'll see how they are written differently. In addition to charge conservation, it's been found that the total number of nucleons must be conserved. So you'll have A on the left-hand side, and then you've got A minus 4 plus 4 on the right-hand side, if you account for everything that's being delivered. So that's alpha decay. Electromagnetic decay. Atomic nuclei have energy levels just as atoms do. And although the levels are much more complicated, when a nucleus undergoes alpha or beta decay, the daughter is often left in an excited state. And there are various ways in which a nucleus can rid itself of this excess energy. It can emit a gamma ray. You can have internal conversion by ejecting an electron from the atom. Note that the electron is the atomic electron and does not reside in the nucleus. It is incorrect, as some texts state, to interpret this as the emission of a gamma by the nucleus, which then ejects an electron from the atom. Instead, the excess energy of the nucleus is transferred directly into the atomic electron. And it's important to understand that this process competes with nuclear de-excitation. In a sample of a radioactive isotope in which the nuclei are in an excited state, some fixed percentage will decay by gamma emission and the remainder will decay by internal conversion. Usually the ejected electron, sometimes called the conversion electron, is a K shell, although L and M shell electrons can be ejected with lower probability. Conversion electrons have discrete energies. Once an atomic electron is ejected, the atom is now missing an electron. So the missing electron causes one of two possible consequences: fluorescence or characteristic X-rays. Electrons cascade down to lower energy unoccupied shells. When they do that, they emit X-rays as well with well-defined discrete energies. And these X-rays have wavelengths that are characteristic of that element. And part two, there are Auger electrons. A vacancy in an inner shell is filled by an electron in an outer shell, and another outer shell electron is ejected from the atom. As an example, suppose that there's a K shell vacancy as a result of internal conversion to K. This vacancy could be filled by an L shell, in other words, one above it, and an M shell electron could be ejected from the atom. The difference, the energy difference between the K and the L shells will be delivered to the ejected M shell electron, providing the energy to eject it and endow it with residual kinetic energy. In other words, you've got enough to escape the atom, and then you got a little change to go with it. There are now vacancies in both L and M shells. They will be filled by electrons from higher energy states, leading to a photon emission or further Auger emission. And then you've got isomeric transition. Most nuclei in excited states lose energy immediately by gamma emission or internal conversion, but in some cases, the excited nucleus has an appreciable lifetime, such a nucleus is said to be metastable, in other words, technetium-99m. So the energy of the gamma is 0.141 MeV, and this isotope is widely used in nuclear medicine imaging studies. So all of those particular reactions all belong to electromagnetic decay. Next is beta decay, and you got three processes that fall under the heading, which are governed by the weak nuclear force. You've got beta minus decay, you've got beta plus decay, and you've got electron capture. Beta minus decay is when the atomic nucleus emits an electron. It's important to understand that electrons do not exist as independent particles in the nuclei. When it undergoes beta decay, the electron is created just prior to the ejection. When it decays by beta emission, each individual nuclear decay may result in a beta of a different energy. Thus, in a sample of a radioisotope that decays by beta emission, the betas emerge with a spectrum or range of energies. There is a maximum energy Tmax of the emitted betas. No betas are observed to have a kinetic energy greater than T max. And the average kinetic energy of the beta particles is given by 1/3 T max. So when a parent nucleus decays to a daughter by beta emission, the amount of energy becomes available, T max. When a beta is emitted with an energy less than that, where does the rest of the energy go? Some energy is unaccounted for. It appears like it's not conserved. This apparent lack of conservation of energy led to an energy crisis in physics in the 1930s. At that time, energy conservation was a long and well-established principle. Physicists resorted to very extreme and creative ideas in an attempt to account for missing energy. And Niels Bohr suggested that perhaps energy is simply not conserved in some quantum phenomena. Wolfgang Pauli said, rubbish, must exist a new particle that carries off the excess energy. To meet the constraints of empirical evidence, Pauli hypothesized that the new particle is neutral to conserve electric charge, and that it interacts exceedingly weakly with matter, which explains why it hasn't been discovered, and carries off excess energy. Saying that the particle interacts very weakly with matter is equivalent to stating that it's extremely penetrating. The average distance that one of these particles can travel through lead before interacting is 4 light years. That's a pretty long time. This particle was named the neutrino by Enrico Fermi, and it means little neutral one in Italian. The symbol for a neutrino is the Greek letter nu. And first, it was believed that the neutrino had a rest mass of 0, but today there's evidence that it has a small non-zero rest mass. Various lines of evidence repeatedly convinced physicists that neutrinos really do exist, but it wasn't until 1956 they were actually detected in the laboratory. The reactions occurring in the core of the sun produce copious neutrinos, and you're consistently bombarded with them. During the day, they come from overhead. At night, they come from below when they pass through the Earth with almost no attenuation. And the generic equation for beta decay, you've got the parent nuclei becomes a daughter nuclei. The proton charge goes up. Number of nucleons stay the same, which must mean that the number of neutrons is going to go down. You've got your beta minus decay there with a neutrino. And this bar over the nu denotes that it's an antiparticle. Even though neutrinos are neutral like photons, the neutrino is not its own antiparticle. In this equation for beta decay, charge is conserved. The number of nucleons is conserved because the A is going to be the same. So some examples of beta minus decay. You can see phosphorus 32 turning into sulfur. You can see strontium 90 turning into yttrium 90. And then you've got yttrium 90 turning into, I believe, zirconium. So unstable nuclei that are neutron rich usually undergo beta decay. Beta decay is a way of getting rid of a neutron. Inside the atomic nucleus, a neutron decays to a proton, a beta, and an antineutrino. Free neutrons also undergo beta decay with a half-life of about 10 minutes. Neutron deficient nuclei undergo positron emission or electron capture. Next, you have positron decay. Positron decay, sometimes called a beta plus decay. The nucleus emits a positron and a neutrino. So here you can see, as before, you have the parent nuclei, you have the daughter nuclei, but what you notice here is that the number of protons goes down 1 as opposed to what it did before, where it went up 1. Positron goes on to annihilate with an electron, generating in return 2 0.511 MeV photons. Photons travel in opposite directions, and this is exploited with PET. Charge and mass number are conserved as always. Note that the other particle emitted is a neutrino and not an antineutrino. In other words, there's no bar there. Positron emission occurs in nuclei that are proton rich or equivalently neutron deficient. And here are some examples. Electron capture. So the process of electron capture is an alternative to positron emission. The two processes compete with one another. Some nuclides may decay by both. Both processes have the same endpoint. In other words, they reduce the Z by 1. Positron decay is more prevalent among lighter elements, whereas electron capture is more common for the heavier elements. In electron capture, an inner shell electron, usually from the K shell, is captured by the nucleus and combines with a proton to become a neutron. If the capture is indeed from the K shell, the process is called K capture. The equation, as you can see there, an example is sodium-22, in which 90% of the atoms decay by positron emission and the remaining 10% by electron capture. You also have it in I-125, which has a half-life of 59.5 days. Following electron capture, characteristic X-rays are emitted with energies of 27 and 31 keV. The Te-125 is formed in another state. 93% of the time it decays by internal conversion, the other 7% by emission of a 35.5 keV gamma ray. So you can see here the types of decay. Here you have the beta minus, in blue you have the beta positive over here in the orange, and then you have the alpha decay way up here. So it's useful to draw diagrams to illustrate the various modes of decay that a nuclei undergoes. So for example, you have the beta minus decay, you have mass energy of a neutral atom. So you see the beta minus going down to the daughter. Beta positive decay, you can see this. Electron capture, you can see that. Internal conversion, you can see this. In figures 3.6, you can see a diagram of, or shows an example of diagrams 2 and 3 above, where sodium-22 decays by positron emission or electron capture to neon-22. Positron emission occurs 90.5% of the time, and electron capture does the remaining amount of time. Neon-22 is an excited state of neon-22, and it decays by gamma emission. 3.7 illustrates the decay of cesium-137, widely used in brachytherapy. Its half-life is 30 years. Approximately 95% of the time, it decays to a metastable excited state of barium-137. In other 5% of the time, it decays by beta emission directly to the ground state of Ba137. This is the decay scheme for cobalt-60. You can see here you've got a beta minus 99.9% of the time. And you can also see that it does have another photon that is emitted even after this one is emitted. The four main sources of radioisotopes naturally occurring produced as a byproduct of nuclear fission, produced in a nuclear reactor, and produced by exposing a material to a charged particle beam from a particle accelerator, such as a cyclotron. And you can see here several different isotopes, the half-lives, therapeutic radiation, and the production. So the Earth and the solar system, you're looking at about 4.5 or 4.5 times 10 to the ninth years old, and therefore elements from which they were formed are at least this old. Any naturally occurring radioisotopes are either remnants of this primordial material or were manufactured by natural processes. There are three categories of naturally occurring radioisotopes. You've got the very long half-life species, you've got the um, intermediate decay products of a decay chain that begin with a long-lived parent, and cosmogenic. Cosmogenic isotopes are produced by cosmic ray bombardment of the Earth. So example is C14, which is commonly used for radioactive dating. An example of a very long-lived isotope is K40. Many natural radioisotopes belong to one of the three decay series. So you've got a series here, the uranium series. You can kind of see some of the parts of it. You've got the actinium series where you can see the beginning and the end points here. You've got the thorium series where again you see the beginning and the end. Okay. Large atomic nuclei contain a large number of protons that must be held together by a strong nuclear force. This force, which acts only on very short distances, has difficulty holding larger nuclei together. If you give a slight push, then the nucleus starts to break into two fragments. The fragments are smaller nuclei, which are more tightly bound, and at the same time, several neutrons will be emitted. Smaller nuclei doesn't want those. This process is called nuclear fission. The push that can send the heavy nucleus over the threshold is an absorption of a neutron. So a neutron can easily enter the nucleus because it's not repelled. The best known example of nuclear fission is U-235, takes in a neutron, becomes U-236, which eventually becomes barium-141 plus krypton-92, and then you got 3 more neutrons coming out. So both charge and nucleon number are conserved in this process. These two values right here are byproducts of the U-235 fission. Others include cesium-137, strontium-90. And you can see here with this decay, you've got FP1 and FP2, and their specific fission product nuclides. On average, 2.5 neutrons are emitted and 200 MeV is released. This appears in the form of kinetic energy of fission fragments, nucleons, and gamma rays. So in a sample of U-235, the neutrons released by a fission reaction can go on to cause other U-235 nuclei to undergo fission. Some of them are lost to the fission process. They either go on to interact in different ways, or they actually escape from the sample before interacting. Suppose the two neutrons on average go on to cause other fissions. You can see that that will have a multiplying effect in a chain reaction. If the chain reaction proceeds rapidly enough, the energy released by the fission reactions will be explosive. If a sample is physically small, many neutrons will escape through the surface and will not cause any further fission reactions. You can kind of see the chain here of what's going on. A sample of U-235 is larger than a minimal mass. A chain reaction will not be possible. The minimum amount of fissionable material necessary for chain reaction is called critical mass. Critical mass depends on the shape of the sample. So the critical mass for a sphere of U-235 is roughly 50 kilograms. Fission fragments are generally radioactive and have many medical applications. They're separated from the fuel rods of the nuclear reactors, where the rods are removed for replacement and are known as byproduct material. Fission fragments usually have a high neutron to proton ratio and are considered neutron rich. And neutron rich nuclei often decay by beta minus emission. So the main impediment to the production of atomic weapons is the manufacture of material that can readily undergo fission. And 99.3% of naturally occurring uranium is U-238. That doesn't work. The remaining 0.7% is mostly U-235. The actual design and construction of an atomic weapon are much less of a technical hurdle. Construction of a uranium atomic bomb requires significant enhancement of natural uranium. The enhancement requires about 90% for weapons grade uranium. No, you can't chemically separate the two. The only way to do it is by exploiting the very small mass difference between them. And a colossal factory was actually constructed in Oak Ridge, Tennessee during World War II to accomplish this task. And one of the preferred methods today is to use gas centrifuges. Uranium is chemically combined with fluorine to produce uranium hexafluoride, which is a gas. The gas is placed in a centrifuge consisting of rapid rotating cylinders. The heavier U-238 becomes preferentially concentrated towards the outer wall, whereas the lighter U-235 is more concentrated near the rotation axis of the cylinder. So repeated enhancement is needed to produce weapons-grade uranium. Neutron activation. A material may be made radioactive by exposure to neutrons. If a material is placed inside a nuclear reactor, it will be subject to intense neutron bombardment. The neutrons may react with the nuclei placed in the reactor to produce a useful reactive material in the reaction. So, production of iodine 125 is done in this process. You can kind of see here the xenon 124 plus a neutron gives you 125 xenon. This with a beta minus decay ends up with iodine 125. So when a large amount of xenon 124 is first placed inside the reactor, there is no iodine 125. Slowly it builds up, and as it does, it begins to decay. Eventually, the amount of iodine 125 becomes large enough that the rate of decay becomes equal to the rate of production. So you end up with a steady state. This occurs after several half-lives of iodine 125, and it's analogous to secular equilibrium. In this case, the isotope is produced by neutron bombardment rather than decay from the parent. Neutron activation is an example of a nuclear reaction. In any nuclear reaction, charge and nucleon number must be conserved. And there's a shorthand way that can be used to represent nuclear reactions such that those discussed above. So for example, the neutron bombardment of P31 can be represented as this. In general, if nucleus A is bombarded by particle little a, resulting in nucleus B and particle little b, it can be replaced or represented as this. So particle accelerator. Particle accelerator is a device that will accelerate charged particles to high energies. The charged particles could be electrons, protons, deuterons. They rely on electric fields to produce an accelerating force. Many different types of particle accelerators, such as linear accelerators, cyclotrons, betatrons, microtrons, synchrotrons. They each have their advantages and disadvantages. The common feature is that they all rely on electric field to exert a force on a charged particle. So an example of production of a radionuclide by a cyclotron is production of fluoride at 18 by proton bombardment. When positive charge is added to the stable nucleus, the product tends to decay either by electron capture or positron emission. And F18 decays by proton emission with a half-life of 110 minutes and is used in PET. Okay, this will be the last section here, radioactive equilibrium. So I mentioned something about secular equilibrium. So this is sort of what we're getting into. Suppose that a radioactive parent isotope X decays to a daughter product D with a parent half-life of T sub P. Further, suppose that D in turn decays to a granddaughter G with a daughter half-life of T sub D. This is a situation for the various intermediate isotopes in the decay series discussed in the previous section. So in some cases, X can decay to more than one species of daughter. The apparent decay rate of the daughter will depend on its rate of production and its rate of decay to G. We will state certain results without proof, but if the half-life of the parent is greater than the half-life of the daughter, then after some period of time, the ratio of this activity of D to the activity of X will approach a constant value, and that is called a radioactive equilibrium. The net rate of accumulation of the daughter nuclei is equal to the rate of decay of the parent minus the rate of decay of the daughter. Now you've got two different types of radioactive equilibrium. You've got secular, and then you've got transient. And this means somewhat greater than, and this means much greater than. So we're going to discuss both of these. With secular equilibrium, this is the half-life of the parent is much, much greater than the half-life of the daughter. So one example is provided by the decay of strontium-90 into the daughter product of yttrium-90. The isotope has been used for brachytherapy treatment of the eye. The half-life of strontium-90 is 28.1 years, and the half-life of yttrium-90 is 64 hours. You can see the prime example of secular equilibrium is a decay of radium in the radon. Radon has a decay life, I think, yeah, it's close to 1600 years, and the half-life of radon is about 3.8 days. So imagine placing some pure radium in a sealed container, which radon can accumulate over an interval of a few years. The rate of production of radon remains constant because radium decays so slowly. Another way of stating this is that lambda sub p times n sub p in equation 3.16 remains almost constant. As the amount of radon builds up, its decay rate increases because of the amount of radon present. And eventually, the rate of decay becomes equal to the rate of production, and the amount of radon present is now constant. Each time a radium atom decays to produce a radon atom also decays. This condition is called secular equilibrium. Secular equilibrium, the activity of the radon will be equal to the activity of the radium. So you can kind of see how the activity ratios here of the different of radon and radium eventually become close to 1. Now, transient equilibrium occurs when the half-life of the daughter is somewhat less than the parent. In the limit in which the half-life of the daughter is much, much less than the half-life of the parent, this becomes secular equilibrium. More important, or an important example of transient equilibrium is provided by the decay of molybdenum-99. This isotope undergoes beta decay to technetium-99 with a half-life of 66.7 hours. The daughter, which 86% of the time is the isomer, the metastable technetium-99, decays by gamma emission to the ground state of technetium-99 with a half-life of 6.03 hours. The remaining 14% of the time, the molybdenum-99, sometimes called moly, decays to other non-metastable excited states of technetium-99. These excited states decay virtually instantaneously to the ground state, emitting a gamma in the process. The metastable technetium is widely used for diagnostic scans. It has a convenient half-life, not too short. There's sufficient time to scan patients after they're administered the technetium, and not too long. The activity in the patient's body will decline quickly after the procedure, so that you do not pose a radiation hazard. The gamma ray emitted is 140 keV. This energy can escape the body and be detected with a device called a gamma camera, which forms an image of the distribution of the technetium-99 in the patient's body. The molybdenum is used in hospital nuclear medicine departments to generate technetium, which is then milked from the generator cow. And that process is called elution. So let's say you start with a pure sample of moly. At first, there is no technetium. After a short while, the technetium will increase as the molybdenum decays. As time progresses, the amount of molybdenum decreases, and therefore the rate of production of technetium metastable decreases. And the amount therefore reaches a maximum value and then begins to decline less and less. Maximum activity is reached after 23 hours. After a long time, the decay curve becomes almost parallel to one another. And when this occurs, this is called transient equilibrium. The activity of the technetium is always less than the activity of the molybdenum because these are the two daughters for molybdenum. Okay, you've got a chapter summary here of many of the things that were discussed. These will be good things to go over. And then you can get to working the specific problems that I will have assigned for you.